Welcome. In this lecture, we are going to talk about ionic bonding, covalent bonding, electrolytes, polarity, and hydrogen bonds. We've got quite a few topics to cover. Let's get started. First of all, the goal of all bonding, you must always remember. And any atom, no matter what we're talking about, when they bond together to form molecules or macromolecules, such as salt or water or a protein, their goal is to have a full outer or full valence shell. If you think back to your electron atomic structure, that means having 8 electrons in your last energy level. Now, the ways atoms can do that is they can gain, lose, or share electrons. Now, only the noble gases on the far end of your chart, helium, neon, argon, group 18, are inert. Means they're unreactive. Means they already have a full outer shell. Everyone else, group 17, 16, all the way back to group 1, have to join up with someone else, gain, lose, or share, in order to get that full outer shell. Ionic bonding, the first we'll talk about, involves a loss and a gain. One of the elements is going to lose electrons and another is going to gain. When an atom gives up an electron, it becomes positive. Remember, in a pure state, it had equal protons, positive, and equal electrons, negative. That means it was neutral. So if you lose an electron, which is negative, you become positive, and a positive ion is called a cation. Now, if an atom that receives the electron or gains it is receiving an extra negative charge, so it becomes negative or an anion. So atoms that are going to give up electrons become positive. Atoms that are going to receive them become negative. And these are our ions, simply atoms that are positive or negative. These are very typical bonds between groups 1 and 2 and groups 16 and 17. The exception being hydrogen at the top, which only has 1 electron, so it's involved in covalent bonds, which are sharing. So if you look in group 1, you see things like sodium. In group 17, you see things like chlorine. And you know that Na and Cl go well together. That's just common old table salt. You may have also heard of NaF here, sodium fluoride. Brushed your teeth with it this morning, hopefully. You can also do group 2 and group 16, because in group 2 they all have 2 valence electrons, and in group 16 they all have 6. So if you give these 2 away, this gives them 8, and if you get rid of 2, then your backup shell has, a full outer shell, so you're good there. Magnesium oxide, MgO, calcium oxide, CaO. You can also do group 2 and group 17, but you got to have 2 of group 17. So you've got to balance out or end up being neutral. So calcium is something that needs to lose 2 electrons. Chlorine only needs to gain 1. But if you had 2 chlorines, they both gain 1. That would be a -2 charge, +2 charge. That cancels out. So calcium chloride, magnesium chloride, all these are examples of ionic bonds. You take a look at what I was talking about earlier. Get backwards here for a second. You look at sodium here, which was in group 1. It had 1 valence electron. Alright, so you've got your 1 valence electron there with sodium, and chlorine had 17 valence, or 17 for a total, or 7 valence electrons. If you take a look at sodium, it needs to lose a single electron. If it can get rid of this one and give it away to chlorine, its backup shell has 8. 2, 4, 6, 8. It has reached its goal. Chlorine only needed 1 more. Being in group 17, it had 7 valence electrons. It just needs 1. So this is a win-win situation. But when sodium loses an electron, it becomes positive. When chlorine gains, it becomes negative. And you've always heard opposites attract. So Na sticks to Cl, and there you go, table salt. One interesting note about these, if you look at sodium, it's a soft, white, shiny metal, very dangerous. It's actually explosive. If you throw it in water, it will catch on fire. Chlorine is mustard gas. A green, yellowish gas was used back in the War of Wars to actually kill people. So both of these are deadly to you. You mix the 2 together, you throw this little piece of metal in here with this green gas and salt. And you sprinkle it on your food. And now it's only deadly to you over long periods of time. Here's a few electron dots for ionic bonding. much easier to draw. Sodium, symbol Na, 1 dot. Chlorine, symbol Cl with 7 dots. Show that the Na goes to the Cl. Na becomes positive, the Cl becomes negative, and that's how you draw it with the electron dot model. Mg needs to lose 2. Now keep in mind, if you knew the Bohr model, if it lost these 2, just like with sodium, its backup shell would be full. So it loses 2 to get full. This one gains 2 to get full. That's why Mg and O work well together. And see, the charges cancel out. +2 and -2. That's how you know it's a good bond. This is why you need 2 Cls down here, because calcium needs to lose 2. Cl can only take 1, but this Cl can take 1. So you get CaCl2, calcium chloride. To make a quick note, ions are vital in the human body. Sodium and potassium are ions that you'll learn that drive electricity in your body. Sodium-potassium pumps are heavily involved in transmission between neurons, sodium-potassium pumps, and muscle contraction. Everybody probably knows calcium's for bones, but calcium has to be there. It's vital for muscle contraction and the release of neurotransmitters. So a dysfunctional chlorine channel is what causes cystic fibrosis. So these ions play major roles in the body, and we call them electrolytes. The word ion and electrolyte are pretty much the same. So you hear about Gatorade, drink your electrolytes. Well, that's just drink your ions. And the reason they do that is because they dissociate in water. When you throw sodium and chlorine together, salt, into water, it dissolves. The ions dissociate, and you've got an electrolyte immediately then. The reason this happens is water's polar. If you look at a water molecule, it's H2O. The structure of it, its part of the water molecule is negative and the other part is positive. So the negative part of water attracts the sodium and the positive part attracts the chlorine because opposites attract, and this breaks it apart or dissolves it or dissociates it. Covalent bonds, key word here, share. Okay, all about sharing. I've always said ionic bonds are kind of, the gain and lose, the haves and the have-nots of a political system. Whereas covalent bonds would definitely be the socialist system where everybody shares everything. If you're going to share electrons, it's not always going to be equal. Sharing is definitely not always equal. And that's where we get that polarity from in water. It's because oxygen and hydrogen share electrons to form water. But they don't share equally. Now, some things do share equally, and those things are called nonpolar instead of polar. If you look at us, we are definitely covalently bonded. Life period is made of 4 major atoms, C, H, O, and N, carbon, hydrogen, oxygen, and nitrogen. You've heard us called a carbon-based life form, organic life. That's because we're based in carbon. It means the structure of all your macromolecules, your proteins, your lipids, your carbs are all based in carbon. So literally, if you were to pick up something living, a grasshopper, yourself, a dog, a tree, 96% of any organic material is going to be made of these 4 atoms, rearranged in countless different ways, all covalently bonded. For example, sugar, C6H12O6, is just C, H, and O. Alright, so all these are just recombinations, C, H, O, and N, everything that makes up life. Pretty interesting. Here's a few electron dots for covalent bonds. You can see hydrogen has 1. You join 2 hydrogens together, that both gives them 2. So remember, the first energy level, all you need is 2. You look at chlorine here, they can share here, fill their shells up. This one's 2, 4, 6, 8. This one would have 2, 4, 6, 8. So everybody's full, everybody's happy. That's Cl2. Water, oxygen's in group 16. It has 1, 2, 3, 4, 5, 6. Hydrogen in group 1 needs to share 1. They do so, that fills everybody up. Both the hydrogens get 2, and they now look like helium because they have 1 level and it's full with 2. Oxygen gets its 8, its outer shell's full. That's covalent bonding at its best. Here's ammonia. Everybody's full, everybody's happy with ammonia. So hydrochloric acid, pretty famous. This one disassociates pretty much completely when you put it in water. That's why it's such a strong acid, because you end up getting a bunch of positive hydrogens out of it. Makes it a strong acid. It's a pretty famous one here, CH4. You can do C's and H's all day long. You can stick a carbon to a carbon to a carbon to a carbon forever and add H's around it. They're called hydrocarbons. Gasoline is a hydrocarbon. This is methane, one of our major fuel sources, also a fart. So pretty common there. A few Bohr models for covalent bonds. You can see the full structure, 2 in the first level, 6 in the second level for oxygen because it has 8 protons. It's got to have 8 electrons. See the hydrogen sharing here, H2O. Methane. Bohr model's far more extensive to draw here. I prefer electron dot just because it's much faster. You don't have to draw all the circles and put everything in there. Polarity comes from when you share unequally. If you look at something like carbon dioxide, it is nonpolar or electrically neutral. The atoms are roughly the same size, so they share equally. You picture electrons in here, and there's a tug-of-war going on between the carbon and the oxygen. It's shared pretty much equally, so it's nonpolar. Nonpolar substances do not react with polar substances well. Oil is nonpolar. Water is polar. Think about what happens when you pour oil and water together. Carbon dioxide, as soon as you crack the lid on that Dr. Pepper, it goes psh, and all that CO2 starts to rush out. You know your Coke goes flat. That's because nonpolar CO2 will not mix with the polar water inside a Coke. Polarity comes from when you have a very large oxygen atom here and tiny little hydrogens. When you do the tug-of-war here, it's not equal. The electrons get pulled much closer to the oxygen, further away from the hydrogen, making the oxygen partially negative and the hydrogens partially positive. That's why if you throw salt in here, the NAs are going to stick to the negative oxygen and the Cls to the positive hydrogen. That's going to break apart NaCl, dissolve it. Water is polar, is very good at dissolving all kinds of things. So here's your definition for polarity, a positive and a negative side. Here's a pretty good example. And you see our hydrogen here, our oxygen here. We're sharing electrons, but notice the electrons are much closer to the oxygen. This is unequal sharing, or polarity. It's a polar covalent bond. Good rundown here, explaining ionic bonding, polar covalent bonds, and nonpolar. Great little chart to review everything. Hydrogen bonding is when you have an atom that is partially, positive and partially negative. So here you have a hydrogen atom. The electrons are close to the oxygen, so it's partially positive. The nitrogen here is bigger, so it's partially negative. When positive and negative come close to each other, they attract and form a bond. And that's called a hydrogen bond. And these are vital in your body. Hydrogen bonding holds together your DNA. It's vital in holding together water, as you'll see in a minute. You notice water and ammonia mix well together. If this was water and this was alcohol, that would mix well together. And if you pour Crown Royal into Coca-Cola, they do not separate. They actually mix quite well. They are both polar. Here's water. Notice how the hydrogen will attract the oxygen atom because it's partially negative, it's partially positive. Opposites attract. You could draw this out, over and over again. You could draw another one here and another one here and another one here. And that's why water tends to form lakes, rivers, ponds, oceans. Even when it falls through the sky, it forms drops. So water loves water. It's attracted through hydrogen bonding. It's a weak bond, but vital in life. This is guanine, and this is cytosine, the G and the C of your DNA. And guanine adheres to cytosine, and adenine adheres to thymine in DNA by hydrogen bonds. It's what gives DNA its double helix structure. This oxygen and this hydrogen, there's a hydrogen bond. This hydrogen and this nitrogen form a hydrogen bond. So there's 3 bonds here, hydrogen bonds holding guanine to cytosine. If I had an image of adenine and thymine, there would be 2 hydrogen bonds holding them together. So DNA, the chemical structure of life, it's what codes for life, period, on this planet, held together by hydrogen bonds.